Hi guys, we are the design of the low-cost respiratory cavity for CFD validation. Our sponsor is Dr. Basu, with our instructor being Michael Tweed. I'm Connor Olson.
And I'm Ryan Olson. So just to get into a little bit of an introduction here, Dr. Basu and his research lab, the Basu lab, have performed prior CFD computational fluid dynamic studies detailing the use and application of intranasal mists and their application. And what they found is that there is a lack of effectiveness of these medications depending on how they're applied. Most notably, the angle at which the tip is inserted into your nose when you spritz the mist. So, as a brief overview of what the anatomy of your nose looks like, your nostrils lead into this big open path called the nasal cavity. And at the back of the nasal cavity is this patch of tissue called the nasopharynx. Immediately behind the nasopharynx are your adenoids, your sphenoid sinus, and eustachian tubes. These three systems are incredibly important when it comes to essentially your nose getting plugged. And so any sinus head cold issues that you have can most easily be medicated and targeted by this patch of skin. As far as the project significance is concerned, just about everyone in this room has had COVID, influenza, a sinus cold, or even just a common cold before. And one of the most easy ways to treat these is using intranasal mists. Now, if we can improve the effectiveness of intranasal mists just by simply creating a simple system for application of these mists, we hope to improve the effectiveness of them. Furthermore, this is just an overall field of study using physical validations of CFD that is currently under researched and underfunded in the pharmaceutical industry as a whole.
So for this project, we have two main sponsor project objectives, with the first being to develop a set of physical experimental models that can be used to validate the CFD models that they have been performing research on. Those CFD models are actually derived off of real patients that have CT scans, and that's where the models are actually derived for those, which we are then using within our physical model. The next project objective for this is just to assist the research assistants through Basu labs so that they can utilize our physical models, our apparatus, our research to continue their research and further transition into better understandings of physical models. We have 4 critical project milestones, with the first being to find a method of buying or creating affordable, highly dimensionally accurate real-world models of the nasal cavity, with the next step being to develop an apparatus for testing those real-world physical cavities, and then the third being to take that apparatus and then develop a way of gathering, piling, analyzing the data from those test apparatus, with the fourth stepping stone to be just to document those findings and then explain our research for further research with Basu. We came up with 3 possible design solutions, with the first option being to simply still model our physical design and then take that, send it out to an outsourced third-party setup where they will then ship a model back to us. The next option would be to do it in-house through FDM 3D printing. And then another option would be to do it in-house, but utilizing SLA or resin printing technology.
So now we can get into why we chose what we chose. We began by building a decision matrix with our criteria being the cost of our model, the model reliability, which reliability is kind of a couple different things baked into one, notably how much can we trust the model that we're getting is a good model? And secondly, how can we trust that the results that we're getting from the model are a good model? So what we kind of baked into that was model transparency. Next, we looked at the ease of manufacturing, how easy or difficult it is to get that, the time it takes to manufacture, the physical accuracy of the model, so this is dimensional accuracies, the model scalability, how big or small we can get it, and finally, repeatability. How many times can we make this model or use this model? Starting at the cost, Our model shop option was quoted to be extraordinarily expensive, so it gets a 1 out of 10, 1 being the worst, 10 being the best. FDM printing got a 10 out of 10 because just about everyone in this room already has an FDM printer. It's just cheap, affordable technology that's ready to go right off the bat. Finally, resin printing got a 9 out of 10 because once you have the printer, it's really cheap, but there's just an initial investment you have to put into it. Next, looking at reliability, the model shop got a 9 because we're paying good money for these models from them. We're trusting that they're going to be reliable, accurate models. The FDM printer got a little bit lower of a rating out of 7 because we're still fairly confident that it's going to be reliable. However, the big issue we have is transparency with FDM printing. And finally, resin printing got a 9 because, again, we're pretty confident that we can get it to perfect accuracy, but there's always a chance that it could go wrong if it's in our own hands. Next, looking at ease of manufacturing, 3D model shop. Pretty easy. We just send them our models, we give them money, and they send them back to us. The FDM printing, there's a lot more work that gets involved. We have to sand surfaces down, we have to polish everything. It has to be a really nice, perfect surface, and it's pretty difficult with FDM. Compare that to resin printing, it's a little bit easier. It's kind of middle of the road. There's still some prep work that goes into it, but it's not getting nearly as intense. Moving next to manufacturing time, the lead time for the model shop was 1 to 2 months between us sending them the model and them getting it back to us. FDM printing could typically be, a couple hours to a couple days, and resin printing for a similar size model is most of the time just going to be a couple hours. So resin printing got the best option on that. Moving next to physical accuracy. Again, we're paying good money for a model from the model shop, so we gave it a 10 out of 10 rating. The FDM printer, we gave the lowest rating because of a couple of reasons. First and foremost, there's model lines or layer lines. So on an FDM printer, you have to extrude each individual layer separately. And typically the smallest layer height you can possibly get is about 0.2 millimeters. Compare that to a resin printer, you can get significantly smaller micron level layer lines, which means that you're going to have far more dimensional accuracy. You're not going to have nearly as rough surfaces for air to pass through while you're testing. Furthermore, the FDM model relies on Z-seams, where it has to start and end each part of the layer. Those seams pile up and they create a nasty edge that should not be there compared to your original CAD model. Moving next to scalability, all 3 did pretty well because we believe that all 3 should be able to go up and down in size pretty easily. There's some constraints to doing it in-house compared to a model shop, but relatively speaking, it should be fine. And finally, repeatability. We gave the model shop a 2 because it's extraordinarily expensive. It has a long lead time, and it just makes it a pain in the butt to get repeatable results compared to the FDM and the resin printer, where the resin printer, if we want another model, we can have it printed the next day. Looking at the actual model costs, the resin printer, there was an initial investment involved of about $600, though depending on when you buy it, sometimes it's $50 to $100 more or less, just depending on what sales are active. Compared, next looking at the recurring costs, this is where it gets expensive. To print a model out of resin, it's about $51 per model, and that's being a little bit conservative, assuming that you're going through an entire 1 liter bottle of resin per model that you make. So assuming that you don't quite do that, you might even end up a little cheaper. And that leaves conservatively 1 week, just depending on who has the printer before you do. Compare that to the purchase cost of the model shop model, $3,000 and 1 to 2 months of lead time. If we extend this out a little bit, we end up that the resin prints equal out in cost with the model shop after 32 resin prints. Furthermore, at 32 outsourced models, you're looking at $96,000 invested. That carries with it an opportunity cost, whereas the Basu Lab has 32 possible models that they could be printing and testing with. They don't have the $96,000 to work with.
And then expanding a little bit further on our one-time cost, we have our actual bill of materials for our test apparatus that we have constructed. As you can see, we were able to source everything quite efficiently, either locally or online, with our vacuum pump only being $100. We were able to shave the price down in some areas like the flow meter, where there could be an extremely precise application for a lab, where we were just trying to get within the range of about 20 liters per minute for our inhaling rates. And then for reference, at just normal breathing rates, the average human takes in about 6 liters per minute, where when you are thinking about actually inhaling for a nasal spray, you're taking in about 20 liters per minute, based on the data that we saw in the research papers, where they had female participants ranging from about 17 to 23 liters per minute. And for our spring project timeline, we started off with a lot of initial research and just understanding our project based on the fact that we are mechanical engineers, and this was a lot more heavily biomedical based, and neither of us had too much experience initially on that. So we spent a lot of time just understanding the project and then figuring out how we were going to go about it within our models and test apparatus. As far as what we had accomplished in the spring of 2024, we had actually developed initial prototype models. As you can see, we then 3D printed them using just Ender 3's FDM technology with simple PLA filament. The one on the left is just white PLA 100% scale, and the one on the right was actually a test using transparent PLA filament. That one is 75% scale, but as you can see, it is not nearly as transparent as we would like to see. We want to be able to identify the colored mist within inside the cavity, and although that would have some light show through that model, you would not, I mean, you can't see the cavity inside, let alone the table behind it. We also have developed a plan for the test apparatus come next semester.
Moving to what we've been working on this semester, we started pretty heavily with just looking back on what we did during the spring, trying to find where we were maybe missing something or where we could improve upon our plans. From there, we moved into actually building our test apparatus and testing. And now we've moved into our final phase, which is just developing our research writing and being able to submit it to our sponsors. So as far as our work has been accomplished, we started the semester by completely redesigning our 3D models, and we did that a couple times. Our first issue was just trying to make our 3D CAD models compliant with resin printing. Resin printing is different than FDM. You're printing upside down, and the typical rules of FDM printing kind of go right out the window. So it was a lot to just kind of relearn how we have to work our models. Second, we had to again redesign when we got to our testing phase, and we found out that the kind of slide and lock technology doesn't work well when you're trying to hold a vacuum. So we had to go in and again redesign our model using O-rings and bolts to clamp it together and create a solid sealing surface to hold the vacuum in all the way up to the nozzle. Finally, we designed a custom test apparatus, as you can see here, using that bill of materials we showed earlier. The custom test apparatus is designed to run air from the vacuum pump all the way up to our 3D printed model, where we are able to input a very precise, finely tuned input angle from our medicine bottle by using a 3D printed, essentially dual gyroscopic measurement. We also used red alcohol ink to dye our mists, because alcohol is not going to degrade or damage the model in any way.
And then in case you noticed on our measuring setup, there's possibilities for hundreds of different tests with just varying degrees and possibilities. So one of our main design concepts that we were going for with this model was just the ease to take it apart and run tests as fast as possible. So 4 nuts, zip them off, 3 pieces come apart, and then for each test, all it takes is to dip it in a little water bath, dip it in an alcohol bath, and we found that the leftover dye comes right out of it, and we were able to perform tests every couple minutes or so. And with those tests, we found that our optimum angle was actually about 50 degrees vertical and straight on horizontally. And in total, that was based on about 60-ish complete tests we had done, where we initially started at a wide range from plus 90 degrees to 0 degrees in each direction, and then from there found our best visual results, narrowed it down, and that's where we came up with these results. This is just another example to show the difference that a slight angle can show within our results. And another thing we actually found that was a little interesting was just the amount of nasal spray that you get out of that one spritz of the bottle. It actually bleeds into a bit of a almost a pool within your nasal cavity. And if you were to tilt your head back, it actually seems to run towards the back of the nasal cavity. And we had not heard of any sort of research happening within this. So we're kind of making note of that for further possibilities, especially for ways to get it into the further back region like the nasopharynx, because all of our tests had kind of the best ones, as you can see, got to about this range. They're hard to see, but that's about where they went. And these are kind of just our references, with the main one being Sue's paper in his research. Any questions?
So is your physical dimensional design sort of a average of all people? I mean, you would want a small one and a large one, or did you decide you didn't need that?
Yeah, so our current physical model is based off of one of the female participants, the exact CT scan of her model that Basu hand selected with us as a decent average from the other ones. Kind of the another purpose of our project is just to be able to print other models per se and just see the differences within the application.
We also have 12 other participants that were recorded, so that would be another future step, is just being able to rerun the tests on the other 12 nasal cavities.
Like a football player with a broken nose?
So they actually had a couple of those that were removed from testing because they were out of the norm.
How many tests would you guess that the research lab would want to run in a year or a study, or how much mileage do you think they'll get out of these?
So I mean, just with ours, even to fully complete the testing we'd be doing, you'd want to run it on another 3 or 4 different participants models alone, just so you can kind of get an average of the data across different studies. So just there 4 additional models, and on top of that, Dr. Basu currently has, I think, 3 or 4 different PhD candidates all running their own tests as well. So multiply that across however many different tests they would be interested in, as well as future studies.
Is your nasal cavity a left nostril or right nostril?
The one we were testing on is the right nostril.
So do you mirror the results for the left nostril, or is it slightly different? You'd have to run entirely different tests.
A little bit of both. It should be in the same ballpark. We were working with about a 5-degree tolerancing or so. So we're hoping that should account for it. But as we go through testing, more subjects will be able to determine if that's still credible.
So with your models, does it account for obstructions? For example, if you're going to use a spray, you're going to use it when you're sick, right? So that means that your nasal cavity is more closed off. Does it account for that?
Our specific cavity does not have any specific obstructions with there. I know like the general instructions for nasal sprays is blow your nose before use. Obviously that isn't going to do or get everything out, but I do know that Basu in their research, they have actually applied some sort of kind of fructose corn syrup type of mixture in some of their research that they're doing to try to simulate mucus, but that's not something that we are applying within our right now.
Okay.
Any other questions? Thank you very much.